In this chapter, we are going to talk about alkenes and the types of reactions that they can undergo, most of which are addition reactions. I want to remind you that alkenes contain double bonds and are found pretty frequently in nature. Here are two examples. This is beta carotene, that's the orange pigment in carrots. And you can see there's many different alkenes here. And then we can also see this is one of the compounds that is isolated from ginger. It's called oil of ginger, and you can see that it also contains alkenes as well. Now, a few things. Alkenes are also known as olefins. So if you hear somebody talk about olefins, they're just talking about alkenes. They're going to contain that carbon-carbon double bond. Now, a terminal alkene has the double bond at the end of the carbon chain, whereas an internal alkene has the double bond not at the end of the chain, but in the middle of the molecule, like here. We can also have cycloalkenes. These contain a double bond in a ring. I want to remind you that the double bond consists of a sigma bond and a pi bond, and each carbon is hybridized and trigonal planar, and it's sp2 hybridized, and the bond angle is approximately 120 degrees. Now, I also want to emphasize that the pi bond is much weaker than the sigma bond, right? Making it much more easily broken. That means that alkenes undergo many reactions that alkanes do not. Now, let's talk about cyclic alkenes for just a moment. Cycloalkenes with fewer than 8 carbon atoms have cis geometry. Right. So if we look at these two, right, cis forms a U shape here, and then trans kind of forms a zigzag shape here. This is trans-cyclooctene. A trans-cycloalkene, just overall, has to have a carbon chain that's long enough to connect the ends of the double bond without introducing too much strain. That's why if you've got fewer than 8 carbons, you have cis geometry, because trans just has too much strain if you go below 8. So this trans-cyclooctene is the smallest trans-cycloalkene that's been isolated, but it is much less stable than the cis version. So this makes it be one of the few alkenes where the trans isomer has a higher energy. So let's just give that some words for a second. A trans-cycloalkene must have a carbon chain long enough to connect the ends of the double bond without introducing too much strain. Okay. Now, let's look at a summary. Here is just a summary of the properties of carbon-carbon double bonds. We have talked about these properties before, but I do like just for us to review them just really briefly. There is no rotation around that carbon-carbon double bond. It's restricted. And so because of this, we name two diastereomers as cis and trans, right? Because there's no restriction, we form diastereomers, we name those as cis and trans. the trans alkenes are generally more stable than the cis because of steric hindrance. If you are here in this cis isomer, there's a lot of steric interaction here. What we also find is that the stability of the alkene increases as the number of R groups on the carbon-carbon double bond increases. And we talked about that in chapter 8. So we can see here an example of increasing stability. Now let's look at how to calculate degrees of unsaturation for an alkene. So a cyclic alkene generally has the structure CnH2n. Alkenes are unsaturated hydrocarbons because they have fewer than the maximum number of hydrogen atoms per carbon. So what happens here is that each pi bond or ring removes 2 hydrogen atoms from a molecule and then that introduces 1 degree of unsaturation. So the number of degrees of unsaturation for a given molecular formula can be calculated by comparing the actual number of hydrogen atoms in a compound to the max number of hydrogen atoms possible for the number of carbons present if the molecule was an alkane that has a straight chain. Okay, so for example, right, let's say we have C4H6 and we want to figure out how unsaturated that is. The first thing we do is we calculate the max number of hydrogens. To calculate the max number of hydrogens, we use the formula CnH2n plus 2. And so this has 4 carbons, so the max number of hydrogens would be 2 times 4 plus 2, which would give us 10. Okay, then we take the 10 and subtract the 6, and that means 4 hydrogens are missing, right? And so that means it's first off unsaturated, right? And so to figure out the degree of unsaturation, there's 1 degree of unsaturation for every 2 hydrogens. So we take 4 and we divide it by 2, and that gives us 2 degrees of unsaturation. Okay. Now, maybe the burning question in your heart is, what about heteroatoms? That's a great question. So when we talk about heteroatoms, there's a few things that we need to do. First, we ignore oxygen, right? This is a divalent atom, right? It's a linker. It has no effect on the degree of unsaturation, so we ignore it. We add halogens. We don't add halogens. We add the number of halogens to the number of hydrogens, okay? And then we subtract 1 hydrogen for each nitrogen that's present. We are going to do examples looking at all 3 of these. So let's go to the next slide to do examples, right? So here's an example with oxygen. We've got C5H8, and this example says, calculate the degree of unsaturation for each molecular formula. So we know if we've got an oxygen, we need to ignore it. And so what does that mean, really? Well, it says, look, this structure then is equivalent to C5H8. And so to figure out the degree of unsaturation, we just proceed like we would for any hydrocarbon. We look for the max number of hydrogens. And so we do that by saying, look, 5 times 2 plus 2 equals 12, right? And then we say, all right, that's the max number that can have. So then we say, let's figure out how many hydrogens have been taken away through unsaturation. And so we would say 12 minus 8 equals 4. So we've got 4 hydrogens that are lacking. We take that 4 and divide it by 2. And we say, now we've got 2 degrees of unsaturation. So that can be a lot of things. That means that this might have a ring, right? Or it could have a double bond and a ring, or it can have 2 double bonds, or it can have a triple bond. So this helps us figure out the formula, particularly when we're doing NMR. Now, let's come up here and look at C6H11 chlorine. When I mentioned the halogen, I said, look, this halogen is equivalent to a hydrogen, right? And so this means we need to add 1 hydrogen. So now the formula would be similar to C6H12 when we're doing unsaturation. So we need to proceed like normal. Our max here is 2 times 6 plus 2, and that gives us 14. We take 14 and subtract by 12 to figure out the number of hydrogens that are missing. So there are 2 hydrogens that are missing. 2 divided by 2 gives us 1 degree of unsaturation. So that could be like a double bond or 1 ring. So there's a lot of options there. Now, let's do an example with nitrogen. So we said, look, nitrogen is equivalent to a hydrocarbon having 1 fewer hydrogen. So with that nitrogen there, you need to subtract 1 hydrogen. So that means this formula would be similar to C8H8. So let's figure out our max number of hydrogens. And so that would be 2 times 8 plus 2. And so that gives us 18. So 18 minus 8 is 10 hydrogens that we don't have, right? So 10 divided by 2 equals 5 degrees of unsaturation. And so that could be something like 2 connected rings with 3 double bonds. So for example, it could be this structure. Right? Where there's a degree of unsaturation for each double bond, so that's 3. A ring is 4, and this ring is 5. So this helps us figure out structures that maybe we don't know, right? And so it's very, very helpful when doing NMR. Now, let's also talk about how to name alkenes as well as alkanols. So when we start talking about naming alkenes, let's do an example. We are going to follow many of the same rules that we have used before. We are going to find the longest chain, right? That longest parent hydrocarbon chain. So if we do that, we look and it's right here. Now, it has to contain the double bond. Right? Then we want to number the carbon chain to give the double bond the lowest number. So that means I'm going to start numbering here from the left. So 1, 2, 3, 4, 5, 6. We can go all the way here. And so we see here that it is going to be with the base name hexane, right? So 3, we need to drop the ANE ending and add ENE to indicate the alkene. So when we do this, right, we also want to give a locant number to tell us where the double bond is. So double bond before the ENE. Okay, so this would be pent 2 ene. Then you want to continue to name using all the other rules, right? So for example, right, we have 1, 2, 3 methyls here. So when we look at this, this would end up being 2, 3, 5 dash trimethyl pent 2-ene. That's how we would name this. Now, a few other kind of quick notes, just so we don't forget. Compounds with 2 double bonds are named as dienes, right? 3 double bonds are trienes, etc. Okay. If when we're talking rings here, right? If one double bond is present, right, the locant is omitted. So we don't have to give the number, right? And it's also understood that the 1 and the 2 bridge the double bond. So what do I mean by this? If we were to name this guy, right, we would number this 1, 2 here, because you want the double bond's a functional group, so it's a higher kind of priority than a substituent. It gets a 1 and a 2. That's where you want to start counting, and you can count clockwise or counterclockwise. However, if you have a substituent, you still want there to be the lowest number. So even though we could have numbered this 1 and 2, we didn't, because that would give the methyl a 2 number, and 1 is lower than 2. So this would then be named as 1 methyl cyclopentene, where we don't put the locant for that double bond in. And remember, locant is just the number. So when I say locant, that's what I'm referring to. Now, let's talk about naming alkanols. So these are examples of alkanols. And these are just compounds that contain a double bond and an alcohol group. Right? And so when you have this, the big rule here is you give the OH group the lower number. So if we look at this, for example, this is prop-2-ene 1-ol. So when we do this, we say, look, there are 3 carbons here, 1, 2, 3. And we could have numbered 1, 2, 3, but we need to give the alcohol the lowest number. The locant for the alcohol goes in between the double bond suffix and the alcohol suffix. Okay, so here's another structure that we have. The longest chain is 1, 2, 3, 4, 5, 6, 7, right? Because it needs to contain the double bond. And so this would be 6-methyl here, hept 6-ene. That tells us where the double bond is. And then 2-ol tells us where the alcohol group is. And so you put both of those locants here between the suffixes. So that's how you name the alkanols there. And you follow all the other rules. Now, let's look at cis and trans, because don't forget, we can also have cis and trans here. When we have alkenes that have an alkyl group bonded to each carbon, like we see here and here, right? We differentiate these using the prefixes cis and trans. Cis has the 2 alkyl groups on the same side of the double bond, and I love alliteration, so I like to say cis same side. That's how I remember that. And then trans has the 2 alkyl groups on opposite sides of the double bond. We've got trans here, showing this alkyl group here and this alkyl group here. But maybe the burning question in your heart is, what do you do when there are 3 and 4 alkyl groups, right? Because we can have double bonds with 3 and 4 alkyl groups, tri and tetrasubstituted. How do we differentiate between those isomers? That's a great question. So we assign the prefixes E and Z to the alkene. And these are based on German words for together and opposite. So we have E here and Z. When we look at this and we go through these steps, you need to assign priorities to the 2 substituents on each end of the carbon-carbon bond using the priority rules for that RNS nomenclature that we learned. So basically, look, you're going to split this here and you're going to compare these 2, and then you're going to compare these 2 to each other. You are not going to compare these and these, right? You don't do that. You're comparing these 2 on this side of the double bond and these 2 on this side of the double bond. So divide the double bond in half and assign the numbers 1 and 2 to indicate the relative priority of the groups on either end, right? If you have your 2 higher priorities on opposite sides of the double bond, that is E. And again, that's for that German word for opposite. Then if you have 2 higher priorities on the same side here, that's for Z. And that is for the German word, which means together. I really, again, like alliteration. And so Z and same and side kind of all sound the same, and cis and all of that. And so that's how I remember it. I also remember it this way, is E here is a vowel, right? And opposite also starts with a vowel. And here, Z is a consonant. Panicked over how to spell consonant there for a second, but Z is a consonant, and so is same, right? And so you put the vowels together and then you put the consonants together, and that's how I remember E and Z. So I want us to do an example of deciding if a isomer is E or Z. So we're going to come here and we are going to look at this guy, okay? And so I am going to compare the priority of this CH3 to that H. And carbon has a higher atomic number than hydrogen, so it is that high priority. And I have one there, but I'm actually going to just say high priority, HP. Okay. Then we come over and now we're comparing chlorine to this carbon. And chlorine has a higher atomic number than carbon, so it's the high priority. These high priorities are on the same side of this double bond. So because they're on the same side, this is the Z isomer. Let's do another example. Okay, let's look at this guy. Now this is tricky because you have to remember, hey, look, there's a hydrogen here and a hydrogen here. And it's going to form that kind of Z shape, and that helps you figure out what that arrangement looks like, okay? So that Z shape is kind of like a context clue. So when we come here and compare on this side, there's a carbon here versus the hydrogen. So again, that's high priority. And then down here, there's a carbon versus the hydrogen here. So that's also high priority. So these high priorities are on opposite sides of the double bond. And so because they're on opposite sides of the double bond like that, they are the E isomer. Now, you incorporate this into the name by putting it out front around with parentheses, right? Just like we did with R and S. So, for example, this is E3-methyl pent-2-ene. Z3-methyl pent-2-ene. So those are the different ways that we can see that. Now we're going to have some common names that pop up as we name alkenes, and so that's just very helpful to be able to recognize those. One of the common names that we're going to see is sometimes we're going to have a methylene group, and so that's just a group that looks like this. A vinyl group is one where there is a double bond separated by the single bond wherever your chain is. And then you can have an allyl group, which is shown like this. The simplest alkene is CH2, CH2. It does not require a number. It would be called ethene. The reason it doesn't require a number is because there's only one place for the double bond to go. But it has a common name. It's also known as ethylene. And so that's used pretty interchangeably, so that's just something to kind of be aware of. Propene. Sorry, I'm just double checking that all my carbons have 4 bonds. When we look here, this would be propene. It also does not get a number because there's only one place for the double bond to go. But it can also be named propylene. And so you'll see that sometimes as well. I wanted to see if there's anything else I wanted to say there. Nope, we're done. So here's a really good example of where you would see a methylene group. So we have our longest chain here. And that would end up being methylene cyclohexane. So if you have a double bond off of a cyclohexane group, then that's where we would use methylene. Same thing with the vinyl group and the allyl group. And so these are the most common places we use these 3 common names is when they are off of a cyclic alkene. When they're off of a cyclic molecule, alkane, alkene, anything that's cyclic there. We spent a lot of time in the previous chapters talking about how to prepare alkenes using elimination reactions. And so I just want to remind you, right, these were in chapter 8 and chapter 9. And these are all elimination reactions. So these are the different ways that we prepared the alkenes, okay? And so we've really gone over that. And so don't forget that. We're still using what we've learned. And then I also want to remind you that the most stable alkene is the one that's formed. And that most stable alkene is called the Zatzev's product, or Zatzev product, right? And that is usually formed as the major product. So I just want to, we talked about this, but I just want to remind you, just a brief review here. When we undergo this reaction, there are two places a double bond can form. A double bond can form here, and a double bond can form here. This is the major product because it is tri-substituted. That means when we look at this double bond, there's 1, 2, 3 R groups around the double bond, and that helps stabilize the double bond. This double bond just has 2 R groups, so it's not quite as stable as this one. Same thing here, right? When we look at this molecule, we can end up with 3 major products, either a mono-substituted here with just 1 R group, or 2 di-substituted. And I want to remind you that the trans is more stable than the cis, and so that's why we tend to get the trans that's formed here. All right, so this ends our introduction to alkenes. We've talked about and reviewed kind of the structure of alkenes. We've looked at how to name alkenes, including E and Z nomenclature, and then we reviewed different ways to synthesize alkenes that we learned in previous chapters, and we reviewed the stereochemistry as well. In the next screencast, we are going to jump into reactions that alkenes can participate in. As always, if you have any questions, please feel free to stop by my office. I would be happy to help.